In the previous video, we talked about the ideal gas equation and we talked about how gases deviate from the ideal gas behavior at states near the saturation region and critical point. But what if we can account for this by using a correction factor? Well, that's what the compressibility factor is. So here is our usual ideal gas equation. And now we add our compressibility factor, and there we go. By using the compressibility factor, we're accounting for the change in behavior of the gases near the saturation region and the critical point. We can also write it isolated for the compressibility factor. Another way we can write it is like this. Here, ideal specific volume is the ideal gas equation isolated for specific volume. If the compressibility factor is 1, then it's an ideal gas. The further away the compressibility factor is from 1, the more the gas deviates from ideal gas behavior. Now gases behave differently depending on the given temperature and pressure. But the cool thing is, they behave pretty much the same when the temperatures and pressures are normalized with respect to their critical temperatures and pressures. We can normalize pressure like this. PR is called the reduced pressure, and we find it by dividing pressure by the critical pressure. The same can be done for temperature. The critical pressures and temperatures are usually listed on the same table that shows the gas constant values. When we find the reduced pressure and reduced temperature, we can look at something called a compressibility chart. Using that, we can figure out the compressibility factor. In the examples we go through, I will go over how to use this chart to figure out the compressibility factor. There is one more thing we need to cover. That's when we're given specific volume instead of pressure or temperature. In that case, we can use something called pseudo-reduced specific volume, or just reduced specific volume. We can find it using this equation. This is probably how it's shown in your textbooks, but we can write it like this without the double fraction. It's very important to note that this value is related to critical temperatures and critical pressures, not reduced pressure or reduced temperature. This value is also shown on compressibility charts, and we will go over how to find it as well. So without further ado, let's go through some examples. In this question, we have superheated water and we need to figure out the specific volume using the ideal gas equation, the compressibility chart, and the steam tables. Let's write down what we know. The pressure is 3.5 megapascals or 3,500 kilopascals, and the temperature is 450 degrees Celsius or 723.15 Kelvin. We also need the gas constant of water, so let's take a look at our table, and that's right here. The first part asks us to use the ideal gas equation to figure out the volume, so let's write it down. Now we can plug in what we know. Solving gives us the specific volume. Next, we need to use the compressibility chart to figure out the specific volume. The first step is to figure out the reduced pressure and reduced temperature, but to use these equations, we need the critical pressure and temperature. So let's take a look at the table. Here we have the values we need. Now let's find the reduced pressure by plugging in our values. Next, the reduced temperature. Now that we have these two values, we need to look at a compressibility chart. Okay, so here we go. First, on the bottom, we have the reduced pressure. Our value is 0.1586, which is right about here. Now see these values? These are the reduced temperature values. So we're looking for a line very close to 1.117, so that would be this one. So where do they intersect? That's about right here, and looking at the left, that gives us a compressibility factor of approximately 0.96. Now we can move on to this equation. Let's isolate for the specific volume. Remember that the ideal specific volume can be found using this equation, which is what we found in the first step. So let's plug in our values and solve. The last part asks us to find the specific volume using the steam tables. So let's take a look at the superheated vapor table. We see that with a pressure of 3.5 megapascals and a temperature of 450 degrees Celsius, the specific volume is right here. Now the question also wants us to calculate the percent error. So we just need to use this equation to calculate that. So that's the real value minus the observed value divided by the real value times 100. This is the percent error for the first value we got, which was using just the ideal gas equation. Now for the second one. This is the percent error for the value when we use the compressibility factor. In this problem, we're told that saturated water is heated until the volume doubles. And we need to find the final temperature using the ideal gas law, the compressibility charts, and steam tables. This is going to be a long one. Let's write down what we know. The initial temperature is 350 degrees Celsius, or 623.15 Kelvin. The pressure is held constant, which means initial pressure is equal to final pressure, and the volume doubles, which means final volume is 2 times the initial volume. Let's write down our ideal gas law that compares 2 different states. Now let's plug in our values. Note that I plugged in the final values in terms of initial values, so P2 is the same as P1 and V2 is 2 times V1. We can cancel them out, so we're left with just this. Let's solve, so the final temperature is 1246.3 Kelvin. The second part requires us to use a compressibility chart. So before we do that, we need to calculate the reduced pressure and temperature. For that, we need the critical pressure and temperature. So let's take a look at our table. Here are the values we need. Now we're given the temperature, but we don't have the pressure at 350 degrees Celsius. So let's take a look at the temperature table for water to find the pressure we need. And that's right here. Now we can plug our values in. First, the reduced pressure. Now, the reduced temperature. Okay, it's time to look at the compressibility chart now. So the reduced pressure is 0.75, which is right here. Now our temperature is 0.96. So the line that is closest would be this one. Now obviously it doesn't really extend all the way down, so I'm going to estimate the path of the line like this. So that gives us a compressibility factor of 0.59. It's important to note that the compressibility factor we found is for the initial state, so when the temperature is 350 degrees Celsius. We will also need the reduced specific volume for this problem. So let's find that from the chart as well. See these values here? They give us the reduced specific volume. Again, I'm going to estimate the path, so it looks like it'll be around 0.76. Now we need to calculate the compressibility factor at the second stage. Now remember, at this stage, the pressure stays the same, but the volume doubles. In other words, the reduced pressure stays the same, but the reduced specific volume will double. This is why we needed that value before. Now we go back to our compressibility chart and find the compressibility factor again. Note that we don't know the temperature at the second stage, since that's what we're trying to find, but we do know the reduced specific volume and pressure. So the reduced pressure is 0.75 and our reduced specific volume is 1.52, which is pretty much the line right here. So looking at the left, we see that our compressibility factor is about 0.885. Now that we have all of these values, how do we figure out the temperature at the second state? First, let's write down the equation for the compressibility factor. Now, we're going to isolate it for temperature. Next, I'm going to write the equation for reduced specific volume. If we isolate this equation for specific volume over R, we get this. Notice how this is now the same, so we can plug this in instead of what we have here. We're finding everything at the second state, so I will add a subscript 2 for the variables. Now we can plug in our values. Let's solve, and that's the temperature at the second state using the compressibility chart. Lastly, we need to find the temperature using the steam tables. To use it, we first need to figure out the specific volume at the first stage, so we need to look at the saturated water table at a temperature of 350 degrees Celsius. Here's the specific volume for a saturated vapor. Again, keep in mind our volume doubles in the second state, but the pressure is the same value we found in the first step. Now we just compare the specific volume along with the pressure to find the temperature using a superheated water table. You will have to extrapolate the values to get an answer close enough, or use the resource I've listed below in the description, where you just plug in the pressure and the specific volume to get the temperature. We get 479.9 degrees Celsius, or 753.05 Kelvin. Let's take a look at one last example. Here, we have CO2 flowing through a pipe, and we need to find the volume flow rate and density of carbon dioxide at the inlet of the pipe, and then the volume flow rate at the exit of the pipe. And we have to do this using the ideal gas equation and the compressibility chart. First, let's write down what we know. The carbon dioxide enters the pipe at 3 megapascals, the temperature is 500 Kelvin, and the mass flow is 2 kilograms per second. At the exit side, the pressure remains constant, but the temperature drops to 450 Kelvin. Since the pressure remains constant, P1 is equal to P2. Let's also write down the gas constant for CO2, its critical temperature and pressure using our table. First, let's find the volume flow rate at the inlet. For that, we can write our ideal gas equation in flow form. Now we can isolate it for volume flow rate. Since we're doing the calculations at the initial state, I will use a subscript 1. Let's plug in what we know. Solving gives us the initial volume flow rate. Next, we need to find the density of carbon dioxide. Let's write down the same equation we used before, which was the ideal gas equation in the flow form. Now we will isolate this so that it's mass flow over volume flow. Remember that density is mass divided by volume, so we can replace this part with density. Let's plug in our values and solve. Lastly, we need to find the volume flow rate of the CO2 as it's exiting the pipe. We're going to use the same equation as before, but this time with subscript 2, since it's the second state. Everything is the same except for the temperature. Solving gives us the volume flow rate at the exit of the pipe. Now we have to do all of this again using the compressibility chart. So first, let's figure out the reduced pressure at state 1. Let's plug in our values. Next, the reduced temperature. We will also do the same thing again, but this time with values at the second state. Since the pressure is the same, we only need to figure out the reduced temperature. Now that we have these values for both states, let's take a look at the compressibility chart. For state 1, our lines are these. That gives us a compressibility factor of about 0.97. Now for state 2, the reduced pressure line is the same, and we can use this reduced temperature line and estimate it to be a tiny bit higher since our value is 1.48. So that gives us a compressibility factor of about 0.96. Now that we have these, we can use the exact same equations we used in the first step, but with the compressibility factor added in. So to find the initial volume flow rate, we can use this equation. Again, notice the only difference is that we now have the compressibility factor added in. Let's plug in our values and solve. So that's our initial volume flow rate. Next, we can find the density. Again, the same equation with the compressibility factor included. Let's solve, and that gives us the density. Lastly, we need to find the final volume flow rate. Remember to use the second compressibility factor for this part. And that is our final volume flow rate. Those are our answers. I hope this helped you understand how to use the compressibility chart and how to utilize the compressibility factor. Thanks for watching and best of luck with your studies.